Okay, so now that we have a little bit of skill taking derivatives, let's go ahead and use it. If you remember when we did the tangent line problem, I said there were several impetuses for the discovery of calculus. One of them was the tangent line problem itself, and then the other one was maximum mins, trying to find values of x to optimize things, right? Finding these places where you had these local mins and max. And of course, we can use the derivative for that because we know that at those local max and mins that are occurring on nice hills and valleys, the value of the derivative is what? 0, because we have horizontal tangent lines. So for parabolas, vertices are easy to find, but for other functions that aren't parabolic, it's not as easy to find the x-coordinates of the vertices. But with calculus, we can find it. That's what we're doing on example 8. Find the coordinates, that means x, y, listed as an ordered pair, and the equations of any horizontal tangent lines to this fourth degree polynomial. Okay? Now, what do we know about this coming in? It's a fourth degree polynomial with a positive leading coefficient. So I know it's going to come in the top and it's going to go out the top, and it can have up to 3 wiggles. Okay? Because it can look kind of like a W. So that's really only thing I know about it. But that also then means that there could be up to 3 places where it has horizontal tangents. So what do we need to figure that out? We need the derivative. So step 1, take the derivative of both sides with respect to x. We get dy dx equals, and now we have 3 terms, so we could just go multiply, subtract, multiply, subtract. Negative 4x cubed minus 4x to the first, and then plus 0. So that makes sense, right? A fourth degree polynomial can have at most 3 local extrema, local max, local mins, because when we take the derivative using the power rule, we reduce the degree by 1, so it becomes a cubic polynomial. So now we show that we are setting it equal to 0, and that's a very important step to, again, show the equation we're solving. And then in this case, we would solve by factoring out. So if we factor out a 4x, we're left with x squared minus 1. And then, of course, that factors as a difference of squares into the product of 2 conjugates. The other thing I want you to note is that I move down. As I move down in solving it, we keep it equal to 0, because notationally, if that falls off at any line, you can lose a check. And now we could just rattle off our solution, 0, -1, and 1. So we just did something very, very powerful. We know now that this local minimum occurs at what value of x? If you look at the number line, right, the 3 values we got in increasing order, the smallest was -1, we have a local maximum at x equals 0, and we have another local minimum at x equals 1. All right, so if this were a first quadrant problem, right, first quadrant problems usually involve physical things because we don't use negative things. So this would be the y-axis, and maybe this would be the x-axis. Maybe this represents costs, right? Cost to produce something, and x is the number of items. We would try to minimize costs, right? As a good business plan, we'd try to minimize costs. And so we'd want to know, well, how many values or how many widgets is usually what they use in economics, just a generic term for something to produce. How many widgets would you want to produce in order to minimize your costs? Well, if you can write an equation for that based upon empirical data that you've been collecting with your company, you could then extrapolate that, in this case, produce 1 widget, and that would minimize your cost. Okay, so maybe it doesn't really fit. That would be one heck of a widget if your company made 1 widget, and that would minimize your cost. Of course, there's other things to consider, right? You want to maximize your profits, maximize your happiness of your employees, and so that's just more variables, and that gets into multivariable calculus down the end. But I don't know if there is an actual equation for human behavior, right? Blaise Pascal, that guy says, love has its reasons, for which reason knows not of. Pretty awesome. Okay. So now we need to answer the question, right? I got a little bit carried away. We just have the x values. It says to find the coordinates of those horizontal tangents. So each of these x values needs to partner up with a y value. So how do we find y values? Plug it into the y value machine, right? Remember, the derivative is the slope machine, and the original function is the y value machine. So we have the point 0, comma. If you plug it in, you get 2. You have the point -1, comma. If you plug that in, let's see, we'll do that together carefully. You get 1. That's going to end up being -2 plus 2, so that's 1. And if you plug in a +1, you get the same thing. This function is an even function. You can tell right away it's an even function because when you replace x with -x, you're going to get the same answer because both x's are even numbers, okay? Which means it has what type of symmetry if it's an even function? It would have y-axis symmetry, yeah. All right, so now the equations, here are the horizontal tangent points, and now the equations of the horizontal tangent lines. What does the equation of a horizontal line look like? Is it x equals or y equals? X equals or y equals? Should be y equals, right? So if they're going to pass through that point, then they have to be those y values. So we'll have a horizontal tangent line at y equals 2 and a horizontal tangent line twice at y equals 1. Those would be the equations. So my graph doesn't quite have y-axis symmetry, but it's pretty close, right? And notice the way I drew it was kind of correct. It didn't actually cross the x-axis, right? We know that it didn't cross the x-axis. So we got a lot of information about that function with just a little bit of work, okay, using the calculus tools that we now have at our disposal. All right, factoring out least powers, moving right along. Okay, so it's important to remember that at any point of tangency, call it x equals c, at any point of tangency for some function f of x, at x equals c, let's just call this right here at x equals c, the function f of x and the tangent line, which I'll call capital T of x, they share two things. Let's draw a tangent line there. How about purple? There you go. There's the tangent line. It's T of x. At any point of tangency, the function f of x and the tangent line T of x share two values. What are they? They share a slope, which means they share a derivative, and they also share a y value, right? They share the x value, right? So at x equals that, they also share a y value, and they share a slope value. They share a function value, and they share a derivative value. Very important to remember that. At any value of x, a function and its tangent line have the same slope, and they have the same y value. All right, let's look at example 9. This is a question that shows up on tests, my tests, AP exams throughout the year, worksheets, and these are the ones that students, when we get further down the year, they always ask me questions. I forgot how to do this, okay? And I can understand why, because it requires a little bit of a setup here. All right, find the value or values of some value k such that this line, 5x plus y equals -9, is tangent to this graph, 2x squared plus kx minus 1. So k ends up being the coefficient of the linear term, which if you know anything about completing the square, this will affect the horizontal positioning of the graph. Just so you know. Okay. So there's some value of k that's going to be able to move this parabola, which opens up, so that it's tangent with this line. Now, if you want to draw a picture, that doesn't hurt, but we do need to have something to work with here. We need to have some equations to solve so that we can find k. So how are we going to do that? I can't really graph this function f of x because I don't know what k is. But I do know what this tangent line is. So I can solve that for y. That might be my first step. Solve this for y, it's -5x minus 9. All right, so if you want to try to make sense of something, visually is not a bad way to do it. So let's at least graph this function and see what we got here. There's -9, and now the slope is -5, so it's going to go up 5. It's going to look something like this. All right, a slope of -5. I have a parabola now that opens up. I do know that because it's a positive leading coefficient, and I want it to be tangent to that line. So now you can just kind of imagine, can you draw a parabola opening up that's tangent with that line? Well, yeah, you can. I mean, I don't know if that's the right parabola, but I can easily envision one there. And, man, maybe I can envision another one down here. Something like that, right? One looks bigger than the other. But notice that I could just shift one over and kind of line it up with the other, like this, right? Kind of matches up. So it's not too hard to envision it, but here's what I can then take from this diagram that can get me started. At those point of tangencies, and there might be more than one, there might be several. There might be more than two versions of it. I could probably draw another one right in here, yeah. So the point of the illustration is just to get you to realize, if it opens up and it's tangent to, at that point of tangency, at that x value, those two graphs share a y value and a slope value. They share a y value first. Let's think about that. If they share a y value, what does that mean about their functions when they're solved for y? They're equal to each other. So that gives me something to work with, the y values. I could say negative 5x minus 9 equals, this one's already solved for y, right? That's what f of x is. It's equal to 2x squared plus kx minus 1. Sweet. So that gives me one equation. I know their y values are the same. Does that one have a unique solution, though? That's one equation with how many unknowns? 2, k and x. So that doesn't have a unique solution. So to find unique solutions, you need as many equations as you have unknowns. I have 2 unknowns. I need 2 equations. How am I going to get another equation? Well, what else do these rascals have in common? Slopes, which means their derivatives are the same. Let's take the derivative of this one. Y prime, of course, is negative 5. That's the slope of that line. And then the derivative of this one, f prime of x is 4x plus k. So let me get rid of this big guy here. So now I could say that they're slope values. Again, notice I'm kind of labeling what I'm doing. The slope values are the same. So negative 5, the slope of the line, has to equal the slope of the function, which is its derivative, 4x plus k. And again, that one doesn't have a unique solution because that's still one equation with 2 unknowns. But if I solve them simultaneously as a system of equations, I can find the unique solution, right? So in this case, I probably would not recommend elimination. Substitution is probably the one that's going to work most often. So of the 2 equations, which variable and which equation should we solve for which variable? What would be the easiest? Yeah, I would notice that down here, I have a single k in that little equation. So let's solve that one for k. All right, we'll solve for k. And we get k equals negative 4x minus 5. So I'm going to put a box around that because we're going to come back to that. Because remember, we're trying to find the k value. But what's going to happen in the intermediate when I plug it back in up there is I'm actually going to get rid of my k. It just so happens that it worked better that way. So negative 5x minus 9 equals 2x squared plus k, which is negative 4x minus 5, times x minus 1. Subbing back in. And now I have one equation with one unknown. So it doesn't look real pretty yet, but I still have a lot of work I can do to clean it up. So let's go ahead and do that. I'll get everything on the right-hand side. So I'm left with 2x squared, and I'll go ahead and distribute this x in there. That gives me a minus 4x squared and a minus 5x. Then I got the minus 1 that was over there. And now if I bring the other things across, it gets plus 9 and plus 5x, and now that equals 0. Or I guess 0 is technically on the left side. We'll do that. So it looks like I brought it over to the wrong side in hindsight, but that's not a big deal. So now that it's completely expanded and everything's on one side, I'll just start combining terms. And I start with the largest degree, so I end up with negative 2x squared. The 5x's cancel, and I'm left with 9 minus 1, which is plus 8. Now, we really don't like leading terms that are negative, and since it's a conditional equation, I'll just multiply everything through by negative 1. So I get positive 2x squared minus 8 equals 0. It's like bringing everything over to the left side. All right, so now since there's only one variable, we can extract square roots. So you can either factor out the 2 and factor, because you're going to get x squared minus 4, which is the difference of squares. Or you could say 2x squared equals 8, x squared equals 4. And in this case, you have to remember to not forget to do what? Plus or minus the square root of 4 is 2. So that's one way to do it. The other way is to just factor it out. And then that's the difference of squares, x minus 2, x plus 2. You're less likely to miss both x values that way, but you do get the same solutions.
In that situation, are you just ignoring the constant 2 up front?
In this situation? Yeah, because once it's set equal to 0, then the zero product property says that either, well, you could also divide through by 2, or you could keep it and say either 2 equals 0, or x minus 2 equals 0, or x plus 2 equals 0. Well, 2 can't be 0, so that's not going to give you a solution, and the other 2 do. Yeah. All right, so I have 2 x values. Now, if this was a multiple choice question, -2 or +2 would be an answer choice. But we're trying to find k, not x. Now, the fact that there's 2 x values kind of implies that maybe there are 2 different parabolas that might work, that give us tangent lines to that graph. We would then need to find the k for both of them. So how would I find the k? Plug it back in over here. Yeah, a lot of wrapping around when you use substitution. So let's go ahead and say when x equals -2, k equals -2 times -4 is +8. 8 minus 5 is 3. And then when x equals +2, we get k equaling -8 minus 5, which is -13. All right, so if this were a multiple choice question, maybe one of those would be an answer choice. It'd say what would be a value of k? Or maybe both of them are there listed in all your answer choices list pairs. So there you go. We had to come up with our own strategy there for finding it. We started by setting the y values equal. Then we took the derivative of each and set the derivatives equal. All right, so y1 equals y2, and y prime of 1 equals y prime of 2. That gives you your 2 equations. All right? And then we solve, and then make sure that you're always answering the question that's being asked. We found the x values first, but then we needed to come back and answer the question by finding k values. So for what it's worth, when you plug both of those values in for k, I have them graphed down here. There's the first solution, and that's the first x value that we found right there. And you can see there's the equation then with it plugged in. And here was the other one at 2, where it intersected it, and that was the equation we got there. So the line's the same, but the 2 parabolas are different. All right? Now, you don't have to sketch that function to make sense of it, but if you ever find yourself kind of wondering what to do first, just sit back, put everything in a graph or a picture, and make sense of it. What do I have? What am I trying to end up with at the end? And how can I put these pieces together to help me get there? Okay? So that's a pretty good question. Multiple steps involved. Any comments or questions on that one? All right. Let's go ahead then and learn 2 new rules. We've got the constant rule, we've got the power rule, and now we have what's called, for lack of a better word or term, the sine and cosine rules. And the sine and cosine rules are the rules for the derivatives of sine and cosine. I know, right? So here it is. The derivative of sine is cosine. And I think we proved that in the notes. Yeah. In 1.4, we proved that in the notes. We set it up, the limit. Well, it was already given to us set up. But we used the composite identity, and we grouped things together, and we came up with cosine. In the worksheet, y'all proved this one. The derivative of cosine is negative sine. Negative sine. They're not each other's derivatives, but kind of, sort of they are, right? The derivative of sine is cosine, but the derivative of cosine is negative sine. Now, here's an easy way to remember it from the very beginning. We're going to have cosine, cosecant, cotangent, inverse cosine, inverse cosecant, inverse cotangent. If it starts with a co, anything with co in the name in this class will be negative. Okay? That helps you remember it. So cosine, I know it's going to be sine, but it starts with co, it's going to be negative. The derivative of cosecant is going to be negative something. The derivative of cotangent is negative something. That's true all year long. And if it doesn't have a co, it's not going to be negative. I didn't even finish spelling anything, did I? I did not. Anything with co, anything, there we go. Anything with co in the name will be negative. All right, so we could prove that, but in the time that remains, I'm going to go ahead and address a question that Mr. Vinagoni had. All right, let's use, let me insert a piece of paper here. Kill an electronic tree. Let's look at the graphs. Okay, this would be kind of nice. There's an x and y axis. Let's go ahead and graph sine first. There's 2 pi, there's pi halves, and some of y'all are maybe getting a little PTSD now, right? Oh, I hated doing this. Graphing sinusoids. Okay, and then here was 1, and here was -1. So let's do y. Y equals sine of x. We'll do it in green. It's Sahala. So axis, high, axis, low, axis, and then working back. Okay. Remember in, was it 2.2, we looked at the calculator problems, and we said the calculator could sketch the derivative of a function and plot it. Okay, and I think we might have done this there too. But we should also be able to do this without a calculator. So if you look at the graph of sine and you start analyzing its tangent lines, on the same graph you could plot what the value of the tangent lines are. Okay, I'll put that right there. So right here, when you launch out of the center of the graph of sine of x, the slope is +1. Okay, we don't have to prove that now, but it's +1. Let's actually start with something else. Right here at the local max and mins, what do we know the value of the derivative to be? 0. So let's do that first. So whatever the graph of sine of x is, I'll use red here. Wherever we have a local max or min, the derivative values, which I'm going to be graphing on the same grid in red, are zeros, right? Now look between, let's go between pi halves and 3 pi halves. This function is decreasing on that interval, so the derivative should be what? Positive or negative on that interval? Negative, so it's going to live below the x-axis. All right, so let's see how it's negative. Instead of trying to stretch, let me bring this down. There we go, smart. All right, there's 0. As I go to the right, it's a small magnitude negative number. And the slopes are getting bigger, negative, until boom, right around there in the middle, where they are the most negative. And then after that, they become flatter again, approaching 0. So right here on the x-intercept, that's where it's going to be the most negative, and that's where it's actually -1. Same thing if I go from negative pi halves to pi halves, on that interval, the y values are increasing. So they start as a small positive number. They get bigger and bigger up until right there where they're a maximum value of 1, and then they start decreasing back towards 0. So that's going to be, say, this. All right, so now you can kind of connect it like this, okay, and it's going to be working the same way. So that's plotting what the slopes are doing. All right, so now that we have that graph, that's the derivative of sine, right, which is what? You recognize it as cosine. So why is the derivative of cosine negative sine? Well, let's graph the derivative of cosine, doing the same thing. Wherever cosine has a local max or min, its derivative has an x-intercept, right? Because it's a horizontal tangent. So it's 0 there, it's 0 there, it's 0 here, and it's 0 there. Now let's look in between them. We're looking at the red graph, right? From negative pi to 0, that function is increasing, yes? So it starts again as a small number, gets bigger and bigger up till +1 at negative pi halves, and then goes back to 0. So at negative pi halves, it's 1. So it's doing this, and then it's doing that. And then notice the red graph from 0 to pi, the red graph is decreasing. So it goes from a 0 to a very small negative to a maximum value of -1 at pi halves, and then they start increasing again back towards 0. So that would be this down here. That looks like that, and then it continues cycling like that. So the purple graph is the derivative of cosine. And do you recognize the purple graph? Well, it starts on the axis at 0, but instead of going axis high, it goes axis low. So if you look at the purple graph and the green graph, they're just reflections of each other across the x-axis. So the purple graph is, in fact, negative sine. Okay. What would the derivative then of negative sine be? Negative cosine. That's where the constant multiple goes along for the ride. You want the derivative of negative sine? It's going to be -1 times the derivative of sine. So it'll end up being negative cosine. I'm not going to draw that on here, but it would start down here at 0, -1. And then coming back full circle, what would the derivative of negative cosine be? It goes back to positive sine because it's negative times negative sine, which becomes positive sine. So these, like the powers of I, they cycle every 4 derivatives. It gets back to where it started. So you get caught in this endless cycle. All right? So if it starts with co, what type of derivative does it have? Negative. If it doesn't start with co and it's trig, what type of derivative does it have? Positive. Okay, we'll stop right there. Enjoy the rest of your fabulous